multi-party computation session. And the first talk in this session is about round optimal honest majority MPC in Minicrypt and with everlasting security. This is work by Benny Applebaum, Eliran Kahlon, and Arpita Patra, and Eliran will give the talk.
Thanks. So, hi everyone. I'll present a joint work with Benny and Arpita. So let's start. So we assume that there are n parties. They can communicate over secure channels, and they also have access to a broadcast channel. And they want to securely compute a function f of their private inputs, and they want to do so in the presence of a computationally bounded adversary that corrupts a minority of the parties. And we assume that the adversary is active, which means that it can deviate from the protocol, and we require full security, including guaranteed output delivery. And in this work, we studied the round complexity of general MPC in this setting. So let me tell you what is known. There is an lower bound of GIKR that showed that at least 3 rounds are required for general MPC. And there are also matching upper bound. So the first one is the upper bound of GRS that showed that it provided a 3-round protocol that required a common random string. And they assumed the existence of a threshold Defici. The CRS was removed in a follow-up work. And the state of the art is the protocol of ACGJ that requires only public key encryption and non-interactive zero knowledge. And in this work, we ask, can we do better? Can we remove the public key encryption and non-interactive zero knowledge? And maybe we can even obtain round optimal MPC from Minicrypt type assumptions. So this is the question. And our main result is a compiler. And our starting point is a restricted class of functionalities called the single input functionalities. So those are functionalities that take input from a single party and then provide the outputs to the rest of the parties. And our compiler takes any 2-round protocol for single input functionalities, where the first round is input independent, it is an offline round, and it transforms this protocol into a 3-round protocol for general MPC, okay, by using only non-interactive commitments. So this is our compiler. And in a previous work, again with Benny and Arpita, we provided a construction of 2-round single input functionalities, assuming non-interactive commitments. The resiliency of our protocol is optimal for a constant number of parties, and it is almost optimal when the number of parties is polynomial in the security parameter, which means that we need a little bit more than honest majority. But now by plugging in this protocol into the compiler, we obtain a round optimal MPC from non-interactive commitments under this, and with the same resiliency as the original protocol. Okay, so this is the bottom line. This is our main result. And now let me say a few words about non-interactive commitments. So there are 2 kinds of non-interactive commitments. The first one is computationally hiding. And if we are using this kind of commitments, then we need security against selective opening attacks. And it is known that such commitments can be based on Minicrypt type assumptions, such as injective one-way functions with sub-exponential hardness. There are other options. Take any assumption from here, and you can obtain round optimal MPC under those assumptions. So this is the first kind of commitments. The second one is statistically hiding. And if you are using this kind of commitments, you actually obtain a stronger notion of security called everlasting security. And this means that the protocol is secure even against an adversary that is bounded during the execution, which is the standard, but can be computationally unbounded after the execution. Okay, so by using statistically hiding non-interactive commitment, we obtain everlasting security for every NC1 circuit and in 3 rounds. And again, it is known that such commitments can be based on Minicrypt type assumptions, in this case, collision resistant hash functions. I should mention that there is a technicality regarding how we select the hash functions. Because the adversary is non-uniform, we need to select a random hash function from the family, and we need to do so before the execution of the protocol. So one way to do it is to use a common random string. We can also have an additional offline round in which the parties select this hash function. And finally, if the adversary is uniform, then we can have a fixed hash function. Good. So those are the results. And now let's see the construction. So our starting point is a 2-round protocol for general MPC that is secure against a weak adversary, a semi-malicious adversary. And this is just an adversary that plays honestly, but can choose the inputs and the randomness of the corrupt parties. We then transform this protocol into a 3-round protocol that is secure against a stronger adversary, a fail-stop adversary, that again plays honestly, but can make any corrupt party to abort at any point of time. And finally, we transform this protocol into a 3-round protocol that is secure against active adversaries. Now, there are known constructions of 2-round semi-malicious protocols, even with information theoretic security. So this is our starting point. And the first transformation from semi-malicious to fair stop is information theoretic. We do not require any cryptographic assumptions. Only the second round requires single input functionalities and non-interactive commitments. And I should mention that our compiler can be seen as the information theoretic version of the compiler of SCGJ, as we will see soon. Okay, so let's start. Like I said, our starting point is a 2-round protocol for semi-malicious adversaries. We assume that in the first round, the parties communicate only over the private channels, and in the second round, they use only the broadcast channels. And every protocol can be transformed into a protocol of this form. So this is without loss of generality. So this is our starting point. And now we want to transform it into a 3-round protocol that is secure against the fair stop adversary that can abort the corrupt parties at any time. And there are 2 kinds of abort. The adversary can abort the parties in the first round or in the second round. And in this talk, I will focus on second round aborts. So what does it mean? Let's take Mr. Brown as an example. It means that Mr. Brown played honestly in round 1, but then decided to abort in round 2, so he did not provide a broadcast message to the rest of the parties in round 2. Again, we would like to securely emulate the broadcast message of Mr. Brown, even if he aborts. And in order to do so, we first need to make sure that all the communication in the protocol is public. This is the first step. And then we will make sure that for every party that did not abort in round 1, the parties can securely compute the broadcast message in round 2. So making the communication public is easy. We add another round, round 0, where we let every pair of parties to exchange one-time pads. And now in round 1, instead of sending private messages, the parties first encrypt their messages using the one-time pads and then send the encrypted messages over the broadcast channel. Okay, so this is essentially the same protocol, but now the communication in round 1 is public. And I should mention previous work used the public key encryption here. We don't need public key encryption, one-time pads are enough. So in the second step, we want to make sure that for every party that did not abort in round 1, the parties can compute the broadcast message in round 2. So let's take again Mr. Brown as an example. And I want you to notice that the broadcast message of Mr. Brown is just a function GI of the inputs of Mr. Brown, the randomness of Mr. Brown, all the one-time pads that were exchanged with Mr. Brown in round 0, and all the public communication in round 1. And then we want to make sure that if Mr. Brown did not abort in round 1, we can recover his broadcast message in round 2. So we let Mr. Brown to generate a garbage circuit of the function GI in round 1 and broadcast it to the parties. He also generates the label. He knows already the input, the randomness, and the one-time pad, so we can release the labels to the parties. And but the main problem is that he does not know the public messages that are sent at the same round. Okay, so we let Mr. Brown share all the possible labels in round 1 among the parties. And the parties can recover those labels in round 2, and in this way use the garbage circuit to compute the broadcast message of Mr. Brown. Okay, so this is the main idea for the fair stop protocol. And now let's move to the active adversary. And here we follow the GMW paradigm, and we just want to let every party prove that he played honestly by using the zero knowledge proofs. And it is well known that single input functionalities capture zero knowledge. So from now on, I assume that I have a 2-round protocol for zero knowledge, where the first round is input independent. Okay, so this is our fair stop protocol. And here's the main idea. We let the parties execute the offline round in round 0. In round 1, the parties prove that they acted honestly both in round 0 and in round 1. Now, because round 0 is very simple, it's fine to postpone the proof to round 1. And finally, in round 2, they do the same. And if some proof fails, that we know that this party is corrupt, and we simply think of it as an aborting party, and our protocol is secure against aborting parties. However, there is a problem, and the problem is that round 0 has private communication. So let's say that, let's say that it's Mr. Pink on the right side. Let's say that Mr. Brown sent a one-time pad to Mr. Pink. Using a private message, it is not clear how Mr. Pink can convince the rest of the parties that he acted honestly with respect to this private message. And so the solution here is to use committed one-time pads. We let Mr. Brown generate a commitment of this one-time pad and send the opening to Mr. Pink. And now if Mr. Pink received the valid opening, then he can prove consistency with the committed one-time pad. And if he received an invalid opening, then he knows that Mr. Brown is corrupt, and he can just send a message of Mr. Brown to Mr. Brown unencrypted over the broadcast channel. So this is the main idea. Let me quickly summarize. We've seen a 3-1 protocol for a general MPC that provides full security under minicrypt type assumptions and with everlasting security, and the version that provides everlasting security. And the way to do it is to use a GMW type compiler for honest majority, where the public key encryption can be replaced by committed one-time paths, and zero-knowledge proofs can be executed by using single input functionalities. And that's it. Thank you.
Questions? I have one question is, are there any other settings where you can foresee transformations for from a single input to a generic?
Yes, so we have a recent work on the statistical regime, statistical security and honest majority, where we have a similar transformation. We're requiring a little bit more from the single input functionalities. We need to perform linear operations we need to perform linear operations over the outputs of the single input functionalities. But yes, in general, a similar transformation works there.
Other questions? Okay. Let's thank the speaker again.
Tests? Yes, sounds good.
So the second talk is sublinear secure computation from new assumption by Elette Boyle, Jeffrey Courtois, and Pierre Mir. And Pierre will give the talk.
So thank you. And hello, everyone. Thank you for being here. So as Shai just said, I'm here to talk about sublinear secure computation from new assumptions, which is joint work with Elette Boyle and Geoffroy Couteau. And let me first reassure you that all of our assumptions are perfectly standard and that any novelty here is only in the context of sublinear secure computation. So with that being said, secure two-party computation allows Alice and Bob to compute a function, here represented as a Boolean circuit C, without having to reveal anything about their inputs, XA and XB, other than the output of the computation, Y. Now we say that the protocol is sublinear if the communication between Alice and Bob is sublinear in the circuit size. So that's the number of gates of the circuit. And the important part here is that the dependency on the circuit be some additive sublinear term. Now, obviously, it would be great to allow Alice and Bob to compute any circuits they'd like, but it's already very well motivated if to allow for computation of a wide and expressive function classes. Now, a natural question you may have is, do we already know how to do this? And the answer is yes. In fact, there are three main ways which yield protocols from a variety of assumptions, either trusted setup or specific structured algebraic assumptions. And what I'm sweeping under the rug here is that not all of these solutions work for the same function classes, but it doesn't really matter for now. Before I can tell you about how we contribute to this landscape, I need to introduce private information retrieval. So we'll see this both as a tool in order to build sublinear secure computation and as a desirable goal in of itself, in the sense that it is a highly specialized form of sublinear secure computation. So Alice has an index, Bob has a database, and the goal is for Alice to retrieve the element of her choice from Bob's database. Now, because it's going to come up later, I'll mention that we can impose a symmetric notion on privacy. So Bob doesn't want Alice to learn the rest of his database. And this task becomes non-trivial as soon as you impose sublinearity in the input size, so sublinearity in the database. And it's so specialized, in fact, that we can hope to achieve very low communication protocols, and there exist solutions in the literature. So now we're ready to talk about what's new. And our contribution is twofold. We have two main results, mostly completely independent, in fact. So the focus of this talk is going to be on the first one. So I'll just say a couple of words about the second. So we achieved polylogarithmic private information retrieval from CDH, and a few interesting things about this. So first of all, it's a computational assumption, which is nice. And the second is that it's essentially the first truly sublinear solution from this assumption of CDH. And finally, an artifact of our construction is that we have to use interaction. So it would be interesting to see if we could bring it down to 2 rounds to match other constructions of polylog pair. But this is all I can say about this for now. And our main result is for sublinear circular computation of the class of layered circuits, which is a very expressive one. So we won't be interested so much in the specific assumption of quadratic residuosity plus learning parity of noise, but rather I'll hopefully convey that we've achieved a new way to break the circuit size barrier. So a new way to achieve this thing. So as Jesper said yesterday, this is essentially a lumberjack convention. So we should all be very excited to be shaving logs and logs. Good. So what we do is we provide a protocol for log depth circuits, and this translates into a slightly sublinear protocol for larger class. So what is this new approach to breaking the circuit size barrier? In a sense, we introduce this tool. We introduce correlated symmetric pair, which is a form of private information retrieval, which allows us to build sublinear secure computation. So in the rest of this talk, I'm going to first tell you how we can use a form of private information retrieval in order to build sublinear secure computation. Then I'm just going to define what this tool is. And finally, we'll sketch how we can hope to instantiate this on the new assumptions, as I promised in the title. So first of all, Alice and Bob are trying to compute a log depth circuit. So what's interesting about log depth is that because each gate in the circuit only has fan-in at most 2, each output only depends on at most logarithmically many inputs. And this is true for every one of your outputs. So what's very good about that is that each of the databases, each of the truth tables of these single output circuits have polynomial size. So this already suggests a way for Alice and Bob to do secure computation. Alice prepares the truth tables and hard codes her inputs in there. And then the goal is, it really looks like private information retrieval. Bob wants to retrieve the element corresponding to his own input. So, it would be a bit of a short talk if we could just treat this as parallel, just as independent instances of pair. And what goes wrong is that if you just run pair for each of those instances independently, you use far too much communication. But we're not dead yet because fortunately, these instances of pair are highly redundant. So they're highly correlated, and that's what we're interested in today. So in the sense that all of the queries Bob makes only depends on his input. So there's some redundancy here. I'll just mention that there was, in previous lines of work on sublinear secure computation, a similar notion was a similar decomposition from this large circuit to these small ones was used. But our contribution here is to view this as a form of private information retrieval. So I want to emphasize that what we are trying to do, we have a single client and a single server, and that these two entities are trying to do a lot of pairs. So if there was no correlation, all of the databases are independent, all of the queries are independent. You can't do much here. So what you might be familiar with is the notion of batch pair, where essentially the client is trying to make a lot of queries to the same database. But this is not what we're interested in today. We're interested in the dual notion. So here's a toy example. The databases are independent, but the queries are highly correlated in a public manner. So what I want to bring your attention to is the fact that you could describe the total entropy used to describe all of these queries is rather small. It's independent of K, the number of databases. So we can hope for a protocol here where the upload communication from client to server is independent of the number of databases. Now, for our application to go through to sublinear secure computation, we're going to need a more involved form of correlation between the queries. And it's a notion we call correlated S-pair with mix and match queries. So recall that each output of your circuit depends on a small number of inputs. And this is exactly how we're going to do our queries. So all of the queries can be described by Bob's input, and a single query to a single database is just a subset of Bob's inputs. So why do we call this mix and match? Well, what can help is to view it this way. So the total entropy of all of the queries is just Bob's input vector. And the way you craft all of the queries is just to mix and match the individual bits of Bob's input. And it's going to be useful in building this notion. So what I can't explain, I mean, it would be a lot of computations, is that if we want to be able to use, so let's say we can instantiate this primitive. Does this yield sublinear secure computation? It does, but we have a very small budget for communication. Essentially, we need constant upload rate from client to server and rate 1 download. So in particular, the amount of communication must scale with the size of with the entropy of the problem, not with the total size of all of the queries, which is much larger. So how can we hope to build this from standard assumptions? So our starting point is to start with a specific construction of symmetric pair and adapt it to the correlated case. So the specific construction is one you may be familiar with. We start with linearly homomorphic encryption. We get oblivious transfer, and then symmetric pair. Now, because, as I said, we are so tight on, we have such a small budget for communication for our correlated S-pair, we are going to have to use rate 1 versions of these primitives of linear homomorphic encryption and oblivious transfer. Now, this can be done, but at the cost of batching, which is going to be a problem in a minute. But the good news for now is that, like, if there exist constructions in the literature of these primitives, of these rate 1 primitives from new assumptions, at least as far as sublinear secure computation is concerned. But the problem with batching, to understand the problem with batching, we have to go back to this idea of mixing and matching. Because what's going on is that what we're trying to do is parallel instances of symmetric pair, and we would like to instantiate each one of them using oblivious transfers. But what the correlation between the queries corresponds to is the fact that some of these oblivious transfers are redundant because the choice bits correspond to Bob's inputs. So what we'd love to do is just to pay communication once in order to do all of our OTs, and then mix and match the OTs we've paid for into these different instances so that overall we have very low communication. Unfortunately, because we considered a batched primitive, it's a monolithic primitive, so there's no good reason why we should be able to decompose our OT messages to retrieve these atomic OTs we need. Now, fortunately, we were able to observe a non-black box property of the construction of Brzekerski, Branko, Dörtling, and Pu, which gives us exactly what we need. Basically, so they have 2 round batch OT. So there's one receiver message from client to server and one sender message from server to client. And the answer, in a sense, the message from server to client, the answer to the OTs is decomposable in the sense that if you look at the structure, you can, like, there is a one-to-one correspondence between the bits of the answer and the OTs you were interested in. So you can, in fact, decompose and everything goes well. Now, I won't have time to go into more detail about this construction. Hopefully, I've given you some clue about the tools we use, and I'll refer you to the paper when it reaches ePrint very soon. So before I leave you, I'll just remind you that, so recall that we have 2 main independent contributions. The first is the one I spent time on, sublinear secure computation for the class of layered circuits from new assumptions. And interestingly, from a form of private information retrieval. So hopefully maybe converging towards some kind of generic assumption. We're not there yet, but hopefully. And the second contribution is polylogarithmic pair from CDH. Now, very quickly, all of this was for the 2-part setting. What happens for the multi-part setting? Well, it turns out that so these are the four approaches we have to breaking the circuit size barrier, and homomorphic secret sharing and correlated S-pair don't seem great for the multi-part setting. However, in new and exciting work, we were able to observe that if you combine the two tools, which on their own are hard to give, like it's hard to use to get multi-party sublinear secure computation, combining them was exactly what we needed to get multi-party sublinear secure computation. So with that, I'll be very happy to take any of your questions, and I'd like to thank you for your attention.
Questions? One question that I had is the pair with correlated queries. Are there any other interesting classes of correlated queries that make it possible to save on the communication?
So for this specific problem, I guess the question is rather whether the specific correlation would have any I guess interesting applications. Because for instance, so if we're just like if the correlation is quite simple, already if we have two-round private information retrieval, an interesting feature of that is that the receiver message is completely independent of the database. And so what this means is that all of the queries of the form, like send the same query to many databases, send like publicly permuted, publicly shifted, I guess, queries to different databases, all can be done with just any two-round pair. So, but we didn't look into into other forms of correlation, but if there are any applications that could be interesting.
All right, thanks, Nika, again. The next talk is about round-optimal black box secure computation from two-round malicious OT by Yuval Ishai, Dakshita Khurana, Amit Sahai, and Agsharam Srinivasan. And Dakshita will give the talk.
Sorry to interrupt. We don't have sound on Zoom.
Sorry, this should be better. And I will.
Yes, thank you.
All right. Thanks. So let's get started. All right. So this talk is going to be about building multi-party computation protocols. The goal in MPC is for a set of players that each have private inputs to compute a joint function on these inputs. Without necessarily revealing or without revealing the private inputs of participants to each other. Sorry, is there a weird noise? Thank you. All right. So the goal is to compute a joint function on private inputs. And the security property that we want is that no colluding subset of players should be able to learn any information about the private inputs of other participants beyond what is revealed by their own implicit inputs and the output of the protocol. It is by now well known that a key building block called oblivious transfer is both necessary and sufficient to build multi-party computation protocols. Oblivious transfer is a two-party primitive that allows a sender to obliviously transmit 1 out of 2 messages to a receiver. In this example, the sender has input S0, S1, the receiver has private input bit B. This can be considered a special case of two-party secure computation, where the receiver learns only SB corresponding to their choice bit B, and the sender does not learn what bit B the receiver has. There's been a huge amount of progress in recent years in understanding how to build multi-party computation protocols from this building block OT. It all started with Yao's work on garbled circuits that gave two-round, two-party computation protocols from any two-round OT. Subsequently, the works of Goldreich, Micali, Vigdersen, and Beaver, Micali, Rogaway generalized this to the multi-party setting. And in particular, Beaver, Micali, Rogaway obtained constant round multi-party protocols starting from any constant round OT. And then in more recent years, this gap of constant versus two rounds was closed by Garg and Srinivasan and Benamuda and Lin that obtained multi-party garbling schemes enabling two-round MPC protocols from any two-round OT. All these constructions either already achieve or can be easily modified to achieve malicious security in the common reference string model. And that's going to be, that model is going to be the focus of this talk. It turns out that in this setting of malicious security in the CRF model, there is still a big gap between what we know to do in the two-party setting versus the multi-party setting. In particular, if we care about black box constructions, where the protocol, the two-party or the multi-party computation protocol, requires only black box access to the next message functionality of the underlying OT. Then in the two-party setting, the work of Ishai et al. Built black box secure protocols for two-party computation from any two-round OT. And on the other hand, in the multi-party setting, all we have are non-black box constructions that really use the code of the oblivious transfer protocol in highly non-trivial ways. So what do we know in the black box setting for MPC? We know that two-round adaptive OT, which is maliciously secure OT that satisfies some extra adaptivity properties, can be used to build three-round multi-party computation protocols. And we also know, so that was by a work of Patra and Srinivasan. And we also know by joint works with Ishai, Srinivasan, and Sahai that two-round OT protocols can be used to build three-round MPC protocols in the random oracle model, as well as two-round MPC protocols in OT correlations models. So these are idealized models that are different from the common reference string model, which is what we care about for the purposes of this work. What this work does is close this seemingly apparent gap, in particular removes the need for adaptive OT from the work of Patra and Srinivasan, and builds three-round MPC in the CRS model that makes black box use of any two-round maliciously secure OT. Now, you may have observed that in the two-party setting, we've been talking about two-round protocols for secure computation. On the other hand, in the multi-party setting, I've been talking about three-round protocols. And there is a reason for this. There's a lower bound of Applebaum et al. That rules out constructions of two-round multi-party computation that for three or more parties that make black box use of a two-round OT protocol. So these results on three-round protocols actually match this lower bound, and it is known that we cannot do any better. So now let me summarize our results. We show that in the common reference string model, two-round maliciously secure OT implies three-round maliciously secure MPC in a black box way. And we also show that two-round maliciously secure OT in a black box way can be used to build what is called two-round, two-sided NISC. Now, let me define NISC. NISC is actually short for non-interactive secure computation. The word non-interactive may be a little bit of a misnomer. This is actually a two-round protocol that allows a receiver and a sender to compute, so two parties to compute a joint function on their private inputs by just sending a single message each. Now, one-sided NISC, where only one of the two parties receives the output, is known from black box use of two-round OT. This was the result of Ishai, Kushilevitz, Ostrovsky, Prabhakaran, and Sahai back in 2011. On the other hand, when both parties want to receive an output, this becomes much more challenging. Now, you may wonder why one cannot just run two one-sided NISCs in parallel. One delivers an OT, one delivers an output to the first party, and the other delivers an output to the second party, So let's just have both parties run these two protocols and then both get outputs and we're done. And indeed, this works in the semi-honest setting, but in the malicious setting, a key challenge is to ensure that adversarial parties use the same input across both invocations of this one-sided NISC. And so we deal with this challenge in this work by using and building on MPC in the head techniques, first pioneered by Ishai, Prabhakaran, and Sahai. And we use these techniques to build protocols that check input consistency via cut and choose mechanisms, and then combine the results to get provably correct and secure protocols. So now let me give a quick recap of the IPS compiler. A key tool or building block in this compiler is an outer protocol that is in the client server setting. It allows two clients that have, sorry, in this example, we'll care about two clients. This can be generalized to multiple clients also. Both clients have inputs, private inputs, let's say X and Y, and they use the help of servers to compute a joint function on these inputs. In this example, again, there are M servers. Each client will secret share their input via an appropriate threshold secret sharing scheme and send these shares to each of the M servers. The servers will compute some function on these shares. What we require for the purposes of our work is that the server's computation should be non-interactive. That means each of the servers should not have to talk to anyone. They simply compute locally on their private shares, recover an output, and then send these outputs back to the clients. The clients that obtain these outputs Z1 through Zm can combine them by running an appropriate decoding function on them to recover the actual output of the protocol, which is some function f computed on their inputs X and Y. In terms of security, this outer protocol, we require it to satisfy malicious security against corruption of one of the clients and a constant fraction of servers. And such a protocol was built in the work of Ishai Kushilevitz and Paskin Cherniavsky in 2010. Now, the way the IPS compiler works is it takes this outer protocol, but then removes the need for these servers by having the clients emulate each of these M servers in their head. What that means is that instead of there being actual physical servers that do the computation, the two clients, the two parties themselves run the next message function of each of these servers by running or by invoking a semi-honest secure two-party computation protocol for corresponding to the function of each of these servers. These semi-honest protocols are often called inner protocols. Now, one important issue here is that a malicious client that is running each of these M semi-honest servers, if corrupted, can actually be cheating in all M executions. And it is important to ensure that that does not happen if we ever want to hope to rely on security of the outer protocol. Because recall that the outer protocol was only secure against corruption of a constant fraction servers. Now, these checks are performed via a mechanism called watch lists. This enables both clients to do cut and choose checks, essentially opening some of these semi-honest secure two-party computation protocols and checking that each of the clients behaved honestly. And by combining carefully the watch lists as well as the inner protocols that are emulating servers for the outer protocol, the work of IPS helps design maliciously secure protocols. Now, in our work, our goal is to build round optimal protocols via this mechanism. So we want to make sure that running all these components in parallel does not introduce additional round overheads. Because of those reasons, we require very specific inner protocols, which are the semi-honest protocols. And in particular, we require them to satisfy some additional properties. The property that we require is an output equivocality property. In the case of two-sided non-interactive secure computation, which is one of our results, it turns out that all we need in order to build an appropriate inner protocol is just instantiate Yao's garbling plus OT with any maliciously secure OT, and that suffices. Similarly, for our multi-party computation result, we build on this work of Patra and Srinivasan, and essentially substitute maliciously secure OT in their protocol to get a robust MPC, which then suffices to instantiate our inner protocols. Another technical difficulty that we encounter is that we require the watch list mechanism to allow the simulator to program ahead of time which executions are going to be watched by malicious parties in the system. This is crucial to simulation for reasons that will require some time to go into, and I don't have the time here. So please go ahead and read our paper. But we built this type of watch list mechanism using ideas from the ICOPS result. I just want to start to wrap up with a different perspective on what we do. So we can think of our work as starting with simple round optimal realizations of two-sidedness and semi-honest MPC that make black box use of any semi-honest OT, and now replace the semi-honest OT with maliciously secure OT in these instantiations. And what we get as a result is a form of robust MPC, which is not fully maliciously secure, but we show via the IPS compiler and a simple application of the IPS compiler that it can be bootstrapped to full malicious security in a round optimal manner. Okay. So with that, I just want to conclude with some open questions that our work leaves. The first is, can we obtain our results by just making black box use of two-round semi-honest OT instead of maliciously secure OT? This appears to be challenging because we don't really know constructions of maliciously secure OT that make black box use of semi-honest OT, and there are certain challenges that one would have to overcome in that setting. Another question is if we can base 3-round MPC on 3-round maliciously secure OT. So this is not something that is ruled out by the lower bound of Applebaum et al. And our work in particular needs 2-round OT. And then a final open question is whether similar results can be obtained in an OT hybrid model. So our work crucially relies on using the next messages that the OT protocol generates. On the other hand, in an OT hybrid model, parties just have access to ideal OTs and cannot necessarily use the next message function of the OT. With that, I would like to wrap up and open the floor to any questions. Thank you.
Any questions?
So can you obtain adaptive security using the same compiler by replacing the malicious secure OT with an adaptive OT? Like,
so it turns out that Patra and Srinivasan already show that if you had an adaptive OT, then that would suffice to build maliciously secure MPC.
no, I mean, like if you want the MPC to be adaptively secure.
If you want the MPC to be adaptively secure, I will have to think about it. Probably, I don't think it would be easy, but I'll have to think about it.
Okay, thanks.
Okay. Thank you.
It's working? Yeah. Okay.
The next talk is scales MPC with small clients and large ephemeral servers by Anasuya Acharya, Karmit Khazai, Vladimir Kolesnikov, and Manoj Pararkawan, and Karmit will give.
Thank you, Shad. Okay, hi everyone. So this talk is about MPC with specialized communication patterns. And this is the recent and very exciting line of work, where essentially we have a large pool of parties or workers that we choose from to perform our computation. And I mean, this line of work is basically driven or motivated by blockchain-based platforms that are becoming more and more popular. Okay. Oh, sorry, wrong way. Okay. So one of the pioneers of this line of works is a paper that introduced the YOSO model. YOSO stands for "You Only Speak Once," and most relevant work to our work. And here the parties basically come online for a very short period of time, and they only produce a single message. So they come and participate in a single round of the protocol. So basically they come online, they've been elected somehow, come online, produce or compute their message, send it to an unspecified receiver, and then go offline. And a notable feature of this protocol is that it allows to avoid adaptive corruptions, which pose a real threat in large-scale and long-term MPC protocols. So YOSO, or this paper, was the first showing how we can avoid such threats. But this model also has some restrictions or limitations. For one, it requires choosing at least one set of committee of parties to perform the next round of the computation. And this adds a slight complication to the protocol because the protocol must introduce such a mechanism. Also, it supports only supports honest majority. So meaning the threshold corruption within a committee, or at least the adversary can corrupt less than half of the parties. And that means that it requires even a stronger or stricter honest majority on the entire set of pools. So the question is whether we can eliminate or avoid these restrictions. So in this paper, we introduced a new model called Scale, which slightly tweaks the YOSO model. In what sense? So we distinct two sets of parties. We have the client, which will be the input provider, and there will be lightweight machines that are not expected to work much. And on the other hand, we have the set of servers, which are the heavy machine will perform the bulk of the computation. The tweaking to the model is that the input providers or the clients are going to speak twice, once at the beginning of the protocol and once at the end of the protocol. And that will buy us a lot of mileage in a sense that our protocol we're going to construct in this model will actually support this honest majority. It will be sufficient that only a single server will be honest. We're going to rely only on a bulletin board, no setup assumption. And you can think of it maybe as a sort of the minimal assumption in MPC protocols that replaces point-to-point channels in the traditional MPC protocol. And for some applications, we might even do with a constant number of servers, even as small as 2. So that's great. I mean, I'm going to talk about scales in this presentation, but there are other applications that we consider in the paper, so you can see the paper for more. Okay, and in order to construct a scales protocol, we define and construct 3 building blocks, which I'm slightly touched in this talk. We have a strong key and message homomorphic encryption, which I'll explain a little bit later. Re-randomizable Garland schemes, which is the main building block, and incremental decomposable randomized encoding. I just want to say that these abstractions help also to fix a small bug in a proof of a previous work by Gentry et al., which we also rely heavily in our work. Okay, so just pictorially, how does a protocol look like in the scale model? So we have an initial server spool, which could be corrupted to some extent. And we have the clients or the input providers. And to run a Scales protocol, they will start by publishing their first message on the bulletin board. This message depends on their input. Next, we have a sequence of servers being nominated or nominated themselves. And coming up, reading the content of the bulletin board and publishing their message. And then after this is done, the clients publish their second message. And out of all this data on the bulletin board, it could be publicly, the decoding of the function's input could be publicly extracted. So our protocol achieves semi-honest security. And in terms of security features, as I was saying, we support honest majority, dishonest majority. We only require a single corrupted server, no restrictions whatsoever on the clients. They can also collude with the servers. And for the servers, we also achieve the Yosso style adaptive corruptions, while the clients could also be adaptively corrupted by plugging in the right building block. So we're using OT. If you're using receivers adaptively secure OT, you can get adaptive security. And in terms of features, just to summarize what I was saying, one honest server overall is sufficient. You could do also with a constant number of servers. Each server publishes a single message, and it's also compatible with random self-selection process, so a server can nominate itself. It's fine as long as an honest server, within this process, also nominated itself. And for the clients, as I was saying, their computation is small in a sense that it is only proportional to their input size and the number of servers, but not the number of clients. And they, a useful feature, they can actually agree when to, or dynamically control when to publish their second message, and therefore end the process made, or the computation made by the server. Good. So let me introduce our main object for Scales. Re-randomizable garbling schemes. Let's start with what we are familiar with, garbling schemes, and recall the abstraction by Bellar et al. So we have, let's say, very roughly two main entities, a garbler and an evaluator. The garbler basically takes a description of the function and outputs some sort of encoding of this function, and also the input encoding, right? It is the encoding of the input to the garbling scheme. And the evaluator will take the function encoding and an encoding that depends on the input, and will produce, or the evaluation phase will produce the output. Well, specifically, we care in this work about projective garbling schemes, where the encoding of each bit in the input is independent. Okay, so what are re-randomizable garbling schemes? Now we add an additional entity, a re-randomizer. This re-randomizer takes an encoding, a function encoding, and outputs a new one, a fresh one. It also outputs, you see this is pi. Pi is some transformation that should be applied on the input encoding. Security-wise, we want this re-randomized garbling scheme to look fresh or to look indistinguishable from a fresh garbling, even if a garbler and an evaluator collude. And so one way to think of randomizable garbling schemes, think of it as a distributed garbling, but of the special case of distributed garbling where randomness is indeed secret shared among the parties, but the process to generate the final garbling is sequential. So this is what this is maybe the source of the name of incremental randomized encoding, because there's some incremental process that each party adds or contributes its own randomness to the final garbling scheme. Good. Okay. So constructing such an instance has been shown already or appeared in the literature in the same Gentry, Halevi, Vaikont, and Nathan paper. Implicitly, I mean, they call it re-randomizable FCP. And let me describe the construction here. Okay, so when we have a garble circuit, basically we choose 2 labels or 2 keys per wire. Right. Good. Now, if you recall, the way like classic garbling schemes work is that every pair of input keys or input labels are used to encrypt the corresponding output label. The output label that corresponds to the result of the computation on this particular gate. So we have a set of ciphertexts, and now we want to re-randomize them. So what do? You use homomorphic encryption, right? Because it has re-randomizing properties. Not that simple, because you need to recall that each label plays 2 roles in a garbling scheme. It plays a role of a plaintext, and it plays a role of a key, right? So if you want to randomize a ciphertext or a gate, we need to make sure we randomize both the plaintext and the keys. So, so that's why we need both the keys and the message to be homomorphic with respect to the encryption scheme. I just want to say we don't need fully homomorphic encryption because it sometimes confuses people. They think we need something that strong. No, it's sufficient. We need a much weaker notion. Additively homomorphic encryption is enough, but the extra property of key re-randomizations is required as well. So now, if you take a look, so basically, the re-randomization process works by applying a transformation on the both the input labels and the output labels. And this goes gate by gate in the re-randomization process. I'm neglecting a lot of technical details how it is done, but just imagine there is a class of transformations that could be applied on this set of ciphertexts, creating fresh ciphertext. And if we're going back to our picture of RGS, randomizable garbling scheme, we also need to provide or need to make sure that we apply a consistent transformation on the input encoding. So so how do you do that? So remember, everything is going to be on the bulletin board. So as part of each encoder's message, it will provide the encryptions of the input labels to the garbling scheme. So these ciphertexts are going to be re-randomized along the process as well. So here we say, if you look at here, what we say basically, the keys that are used to encrypt those labels are basically what we're going to use as inputs to the OTs, right? Somewhere there's going to be an OT that will allow the client to obtain the corresponding input labels so that later someone can evaluate the final Garbon scheme. So these keys that encrypt the input labels will be set as an input to the OT phase. And now, by the way, this encryption scheme is slightly weaker than what we need to the actual Garbon scheme, because here we only encrypt the input labels. And as part of re-randomizing the Garbon scheme or this transformation, the server, or each server, also applies the corresponding transformation on this set of, right? So here, if you have a set of ciphertext, first we apply the transformation on the set of plaintext and then on the set of keys.
Commit.
Okay, sorry, wrapping up. So let me skip protocol and so just one sentence. Performance-wise, there is a trade-off between YOSO and scales, computation and communication, and number of rounds. See everything in the paper. Open problems. This paper leaves a lot of open problems. How to construct better schemes, achieve stronger security, and even go below maybe constructing sublinear re-randomizing schemes. Thank you.
Okay. So I think we'll take the questions offline.